All right, welcome to Kinetics 3 lecture notes. Sorry I'm a little late getting these posted. This is going to be kind of piecemealed together because this particular set of notes has some good stuff in it, but I prefer a different set of notes, so I'll be splicing some different things together to get all the information we need. In terms of this particular set of notes that came from AP Chem Solutions, I'm going to focus in on the factors that affect reaction rates. We're going to talk just a tiny bit about activation energy. I'll skip through some of the slides because they are overkill for what we need to know in this course. And then we'll switch to a different set of notes to cover reaction mechanisms, and then we can talk about catalysts as well. So, in order for a reaction to happen, the reactants have to collide. They have to bump into each other. And they don't just have to bump into each other, they also have to meet these second two conditions. They have to bump into each other in a certain way. Usually we say with proper orientation, and I'll have a picture here in just a minute that kind of describes that. And then they also have to bump into each other or collide with enough energy that they can get over what we call activation energy. And we're going to talk about that in a sec as well. So there's a few things we can do to increase the rate of collisions, and by that then you could also deduce the things you could do to decrease the rate of collisions. But the way we can increase the rate of collisions, if we have stuff in the liquid or gas phase, by increasing concentration, that means you're putting more moles of reactants together in a container. And so by doing that, you're increasing the likelihood that they're going to collide. And you're also increasing the likelihood that they're going to collide with proper orientation and with enough energy to overcome activation energy. So by increasing concentration, specifically in liquid or gas phase, we're increasing the fact that those collisions are going to happen. If we're talking about a reactant that's in solid phase, if we increase that surface area, you're just providing more locations for collisions to happen. So if it's in solid phase, then by crushing it up, not leaving it as a solid cube, crush it up into smaller pieces, that's going to increase the surface area. That can increase the rate of collisions. And then lastly, if temperature increases. So remember, temperature measures kinetic energy. So if we cause the molecules to have greater kinetic energy by increasing the temperature, supplying heat to a reaction, then those molecules are going to collide more frequently, as well as with a greater amount of energy. And so that is some of the ways we can increase collision rate. So here's a picture talking about orientation and why it's important. So if I have this reaction, 2NO2Cl yields 2NO2 plus Cl2. If a molecule of NO2Cl collides with another molecule of NO2Cl like this, in this particular orientation, this orientation does not produce products. They have to collide where the chlorines hit head on, because those chlorines have to be able to stick together to produce that Cl2 molecule. Now, all of this is going on at the same time, but only the molecules that collide in this particular orientation for this reaction are going to be able to produce products. So that's one of the things that has to happen. They have to collide with proper orientation in order to produce products for the reaction to occur. Another thing that has to occur is they have to overcome activation energy. And so this is kind of a generic reaction profile, and I'm going to skip to this slide so I can simplify it a bit. So on the left, if we imagine we have our reactants, AB plus C, and on the right, we have the products of this reaction, A plus BC. In order to get from reactants to products, there has to be an input of energy. The energy to get the reactants up to products, there's an increase of energy. Something has to supply energy to this reaction to get it going. Sort of like when you take a match, it doesn't just automatically it doesn't light itself when you remove it from the box. You have to supply some energy and strike it on the little strike sheet to get the reaction started. And once the reaction starts, then we get products. We talk a little bit more about being able to look at one of these reaction profiles when we get to thermochemistry, but you should be able to kind of understand that if the products end lower than the reactants, what that means is getting over this hump. That's the activation energy represented by E sub A. So the hump is the activation energy. So this is how much energy had to be put into this reaction. And then the reaction starts to go or starts to proceed, and we get an energy output. Now, once we get to this point on the graph, we have recouped all of the energy that we put in for activation energy, and then we get more. And so that is an example of an exothermic reaction. If I was looking at an endothermic reaction, I would see that this reaction would start. I would input my activation energy, and then it would stop and stall and finish somewhere higher than the reactants. And so what that means is I had to put in a certain amount of activation energy, but I didn't get all of that back. That's an endothermic reaction. Okay, this is an important concept for you guys to understand. This is called a Maxwell-Boltzmann distribution, and I sure wish I could draw on this, but I can't in the program I'm using. But what you got to imagine is the area under the curve. So let's just talk about this green line. The area under this curve, that represents all of the molecules, all of the reactants that are colliding, all under this curve. Same thing with the purple. The area under that curve represents all of the reactants that are colliding, trying to make products. And this is the same reaction for both the green and the purple line. So the area under the curve for the green is the same as the area under the curve for the purple. Like if we took a ruler and we really measured all of that out, we would find that those two things represent this. It's the same area. What this graph allows you to do, it allows you to interpret what happens to a reaction at varying temperatures. So the purple line represents what happens at 500 K. And an important marker here is this dotted line labeled EA. And again, that's activation energy. So what this means is there's all these collisions happening under this curve, but only the collisions that occur to the right of this dotted line have enough energy to actually produce products. So over here, this is all of the reactions that are actually making products. We have lots of collisions occurring, lots of reactants doing their thing, but these are the only ones that actually make products because they're the only ones that have enough energy to get past that activation energy threshold. If we increase the temperature from 500 to 1000 K, notice how this line kind of pulls off to the right. Imagine if I took the end of this purple line and drug it this way. I just pulled it this way so that it aligned with the green. That's increasing kinetic energy. When I move it to the right, that's increasing temperature to the right. So now we have all of these guys under the green curve colliding, but not colliding with enough energy to get past this activation energy threshold. And so one of the things you should be able to analyze here is the fact that at the higher temperature, I have a greater area under the curve for that 1000 Kelvin than I do at 500 Kelvin. So there's a couple different ways that you could be asked to analyze this graph on a test question. They could not give you these temperatures and ask you to label which one is which, as in which one is the higher temperature and which one is the lower temperature. And so you should know that the higher peak at a lower temperature, that's going to be the lower temperature compared to this guy would be the higher. They could also ask you to shade the area under the curve of collisions that actually produce reactants for a particular temperature. So let's say they say do it for the 1000 Kelvin temperature. Well, then you would have to make sure you shade the area to the right of that activation energy threshold, because these are the only ones that actually produce products. Another thing they could do is they could ask you to sketch another line on top of this graph to show how another temperature relates to the one that they've already provided to you. So maybe they say sketch a line of what you would expect to see at 250 Kelvin. And so 250 is less than 500. So just imagine again what you would see if you took the end of this purple line and you kind of pushed it back to the left, where it's like a lowering of kinetic energy. How would that make this line look? We would see the hump be higher over here, and then it would start to decrease, and we would have a smaller area under the curve. That line would kind of taper off so that we had a very small area under the curve past that activation energy threshold. So that's a couple different ways you could be asked to analyze this graph. And this is called a Maxwell-Boltzmann distribution. Let's skip through a few things. This is a good thing to note. When we start talking about how does activation energy and rate compare to each other, the larger the activation energy typically means you have a slower rate. A reaction takes longer to produce products if it has a large activation energy. Comparatively, if it has a smaller activation energy, that's going to be a faster rate. And there's just a summary of all of the stuff that we just covered. And all of that kind of falls under the blanket term collision theory. Collisions have to happen. They have to occur with proper orientation. And the energy of the collision itself has to be greater than or equal to the activation energy. This is what must occur in order for products to be produced. Okay, so next thing I want to talk about is what's called reaction mechanisms. So a lot of the times when we look at a chemical reaction, in our brains, we see that as happening in one step. And most times they don't actually happen in one step. They happen in multiple steps. And each step is called an elementary process or an elementary step. But when you combine all of the steps together that happen to get from reactants to products, that is called a mechanism. And so this would be an example of kind of an overall mechanism. Step 1, 2, and 3 is an overall mechanism put together. Here's the overall reaction, but in order to get from 2A plus B to produce D, it has to go through 3 elementary steps. So the first step is where A and B and C react together, and the product of that is X. And then X reacts with some A to produce Y. And then Y breaks down to make C and D. Now, if we take all 3 of these elementary steps and we add them together, so everything on the left gets added together and everything on the right gets added together, and then we cancel out like terms that appear on both the left and the right, much like we did in net ionic equations, that's how we obtain the overall reaction. Now, there's a couple pieces of vocabulary you should know. If you have something that is, if you have a reactant that's present in step 1 and then also present as a product in the final step, that is called a catalyst. That helps the reaction go faster by lowering the activation energy, and we're going to talk about that in a moment. But that is how you identify a catalyst. If you have something that is produced in one step, like X, and then it's used up in a subsequent step or consumed in a subsequent step, like it is here, that is called an intermediate. So X is an intermediate. Y is also an intermediate. It's produced in step 2, but then it is consumed as a reactant in step 3. So you should know how to identify catalysts and intermediates, and that's typically a question you see anytime you're asked to work out a mechanism problem. Okay, I think this slide kind of overcomplicates a concept here. What I want you to know is that when you have an elementary reaction, If you think back to early on when I said you cannot use the coefficients in a reaction to determine the rate law, you can't use that to predict the exponent or the reaction order. That is only true for overall reactions. If it's an elementary step or it's one step in a mechanism, you can use the coefficient to determine the reaction order because each step can have its own reaction, its own rate of reaction. And then we have to do some manipulation to figure out which one is the right one for the overall reaction. But notice here, this is 2A producing products. If it's an elementary step, then I can just square or use that coefficient for the rate law. Just like this guy, this would be 3A producing products. Since it's an elementary reaction, I would just say rate equals K A raised to the third. There's another example, 2A plus B making products, rate equals K A squared times B. That is only true for elementary reactions. So make sure when you're working with mechanisms, you recognize that you can do that for those elementary steps, but not if you're working with an overall reaction. Okay, so let's talk about a mechanism. Obviously, it has multiple steps. One of those steps is slower than the others. Whichever one is the slowest step, we call the rate determining step because it's the one that determines how quickly reactants produce products. So this picture is kind of giving you an example. If we have two toll booths, and one of the toll booths in this example, Toll Plaza A, is the type of toll booth where you have to slow down and throw coins in. And then Toll Plaza B is the type that just reads your toll tag. Obviously, Toll Plaza A is the rate determining step. This is where you have to slow the reaction down. It's going to determine how quickly the car gets from point A to its destination. And then inversely, or I guess another example, if Toll Plaza B was the slower of the two steps, then that would be considered our rate determining step. So it's really quick through the first step, but then the second step slows it down. So you have to be able to look at a mechanism and determine which type it is. You're going to have two scenarios. You're going to have a scenario where the first step is the slow step. Those are really easy. To determine the rate law of a reaction mechanism where the first step is the slow step is very simple. So we like those because they don't take very much time. Or we could have a reaction mechanism where the slow step is not the first step, where we have a fast first step. Those take a little more time and require some substitution and some algebra. But you need to be able to tell the difference between the two and understand that there is a difference between the two. And it's usually not that hard because they typically label the mechanisms. So here's an example of a slow initial step. Given the overall reaction of NO2 plus CO produces NO and CO2. Says the rate law is determined experimentally to be this guy. Rate equals K NO2 squared. So second order overall. So here's a proposed mechanism. This is the mechanism that we think this happens by. We think that NO2 collides with some more NO2 to produce NO3 and NO, and that is the slow step. And then that NO3 collides with some CO to produce NO2 plus CO2, and that is a fast step. Notice the slow step is labeled, and it would be for you. So if the slow step is labeled, then we know that this is the rate determining step. Before we move on, pay attention to the fact that we do have an intermediate. We have an intermediate of NO3. It's produced in one step and then consumed in a future step. So that is an intermediate and it goes away. And also that CO is not part of the rate determining step, so we would expect CO not to be in the rate law. And so that is consistent with that rate law that's provided here. So we just write a rate law for the slow step for this overall reaction, which is rate equals K, and then the reactants, NO2, but there's two of them. And so the coefficient is 2, and then we square it. And so since the first step is the slow step, then this rate law matches the rate law for the overall reaction because we're basing the rate law for the overall reaction off the slow step since it is the first step. When we have a fast initial step, there is more work to be done. So here is the proposed mechanism for that. So we have NO plus Br2 produces NOBr2, and this is labeled as the fast step. And you should note that this is a two-directional arrow, and we haven't covered equilibrium yet, but all that means is that these reactants produce this product, but then this product turns around and goes back to these reactants. And the rate at which that happens is equal. So the rate at which NO and Br2 are producing NOBr2 is equal to the rate at which NOBr2 is going back to produce NO plus Br2. So then the NOBr2 reacts with some NO in the second step, and that is how we get our overall product. Okay, so here's our mechanism, and obviously we have that fast step first and then the slow step after. And what's actually important is that we notice that the fast step is also in this two-directional system. So we have equilibrium. So when you have your slow step being after, the first thing we're going to do is we're going to write the rate law for the slow step. And that's easy enough because we already know that since this is an elementary step, we just use the coefficients, which in this case are just 1. So we say rate equals K, NOBr2, and NO. So that is the rate law for the slow step. But the problem is NOBr2 is an intermediate, and you cannot have an intermediate in your rate law for the overall reaction because there's no way to measure that. So if we looked at what the overall reaction was, we just combine like terms and get rid of the intermediate. So we have 2 NOs. So I'll write that up here. 2 NOs plus some Br2. The NOBr2s cancel out, and then the product of this is 2 NOBrs. So this NOBr2 intermediate isn't in this overall reaction, so there's not going to ever be an opportunity for me to measure the concentration of this. So I'm not going to be able to do a rate law that contains that. And that's why we have to do some extra substitution steps. So then the second thing we have to do is write the forward and reverse rate law for the fast step. And we're actually going to set them equal to each other. So if I look at this fast step, going in the forward direction, the rate law for the fast step going in the forward direction would be rate equals K, and I'm going to do a sub F because it's going in the forward direction, times NO and times Br2. So that's the reactants here. And then I'm going to do the same thing, but consider if I rewrote this reaction going in the reverse direction. So now this becomes the reactant. And I'm going to set it equal because that's what this two-directional arrow means, is that we're in equilibrium. So the rate at which we proceed to the right is equal to the rate at which we proceed to the left. So I'm going to say K, and then R for reverse, and concentration of that NOBr2. So that is the rate law for the forward and the reverse direction of the fast step. Next thing I'm going to do is rearrange this thing to solve for the intermediate, whatever it is that I can't have in my overall rate law. So I'm going to rewrite this equivalence that I just made, this rate equivalence factor, and I'm going to rewrite it so that it just says NOBR2 equals everything else. And so in this case, that's really easy. I just need to divide through by K sub R and put it over to this other side. So I'm going to keep my K's together, and I'm going to say KF divided by KR, and then times NO times BR2 equals NOBR2. So all I did was take the intermediate, the thing that I've already said I can't have in my slow step, whatever the intermediate is, and I'm going to take that from my fast step, and I'm going to rearrange my fast step so that it says whatever that intermediate is isolated on one side. So it says NOBR2 equals everything else. So the next step now is to substitute and simplify. So when I say substitute, I'm going to take this entire term and I'm going to substitute it into my rate law for my rate determining step where that NOBR2 is. So I'm going to put all of this plugged in right there. I'm going to rewrite it. So I have R, and again, I'm going to gather all of my K's together. I had that original K, and I'm multiplying it by KF divided by KR. And then the rest of this, NO and BR2, as well as that NO. Okay, so that's the substitution. Now we have some simplification to do. Anytime you have a constant times a constant divided by a constant, that's just another constant. So I'm going to simplify this whole thing and call it just K. So that's just new constant K. It's constant for the overall reaction instead of constant for the first step. I should have written that in there. Rate constant for the first or for the slow step versus constant for the fast and the reverse step. So all of that put together makes new constant K. And then I'm going to simplify some of these terms. So I have NO times NO, which means I got NO squared, and then multiplied by that BR2. That right there is the rate law for the overall reaction. All right, last thing we got to talk about is catalyst. So we already know, hopefully you already know the definition of a catalyst is that it makes a reaction go faster. Well, the reason it makes a reaction go faster is because it lowers the activation energy, causes a decrease in activation energy. And what that really means is that it changes the mechanism. So in this graph, the red line represents a reaction that is uncatalyzed. We have hydrogen peroxide producing water and oxygen gas just by natural decomposition. And typically this activation energy, this hump, is by light. So exposure to light causes this reaction to decompose into these products. That's why hydrogen peroxide has a shelf life that's not very long and why it's kept in a brown bottle so that we can reduce the amount of light that affects getting over this activation energy. We can cause that decomposition to occur faster by adding some catalysts. And in this particular example, they're saying if they add some ions of bromine and some hydrogen ions, then we lower the activation energy. So notice that the activation energy is less. These humps are lower. The overall output is the same, like this ends in the same place. It just doesn't take as much energy to get started. Now, a couple things that I want you to take note of in this particular graph. The reason there are two humps here is indicating that this is a two-step mechanism. So we have step one occurring right here, and then step two occurring right there. And a question you could potentially be asked about a graph like this would be if these humps were labeled. So let's say this was labeled as step 1 and this was labeled as step 2. You could potentially be asked to determine the rate determining step. Now remember, the rate determining step is the step that requires the most activation energy because it's going to be the slowest step in the mechanism. So step 1 would not be the rate determining step because that requires a very small amount of activation energy. But step 2 requires more. So this is going to be our rate determining step in this catalyzed reaction.